Heating aluminum to high temperatures until it melts into a liquid is a crucial step in the traditional process of making aluminum pots. The process begins with solid aluminum pieces, often sourced from scrap or recycled materials, which are placed into a heat-resistant crucible. The crucible is then heated in a furnace, which can reach temperatures of around 660 degrees Celsius, 1,220 degrees Fahrenheit, the melting point of aluminum. In rural setups, the furnace might be a simple but effective setup, fueled by coal, wood, or gas. As the temperature rises, the aluminum gradually changes from a solid to a molten state. To ensure uniform melting, workers may occasionally stir the aluminum with a heat-resistant rod, breaking up any clumps and eliminating air pockets. Once the aluminum reaches a fully liquid state, it appears as a silvery, shimmering pool inside the crucible. Care must be taken to remove any impurities or slag that float on the surface, using a skimmer to ensure the final product's quality. Setting up the molds involves carefully positioning them to shape the molten aluminum into the desired pot form. The molds, often made from cast iron or steel, come in two parts: the outer mold for the pot's shape and the inner mold to form the cavity. Workers ensure the molds are clean and free of debris to avoid defects in the finished product. They then align the molds precisely, securing them on a stable surface to prevent shifting during the pouring process, ensuring consistent thickness and quality. Securing the molds firmly is a critical step to ensure they remain in place during the pouring of molten aluminum. Once the molds are aligned, clamps or locking mechanisms are used to hold the two parts tightly together. This prevents any movement or separation when the liquid aluminum is poured in, which could lead to leaks, uneven edges, or other defects in the final pot. In traditional settings, workers may use manual clamps, bolts, or weights to keep the molds tightly secured. They might also reinforce the molds with a surrounding sand or clay mixture to provide additional stability and insulation against the heat. Ensuring a tight seal between the molds is crucial, as it prevents the molten aluminum from seeping out and maintains the desired shape and thickness of the pot. Steady hands. Using a ladle or a pouring spout from the crucible, workers carefully transfer the molten aluminum into the mold's opening. The liquid metal is poured slowly and evenly to avoid splashing and ensure it fills all the cavities completely, creating a uniform shape. After pouring the molten aluminum into the molds, excess metal may accumulate at the top, forming a layer known as flash or overpour. Workers quickly remove this excess aluminum before it solidifies, using a scraper or metal rod to skim it off. This step ensures a clean and uniform finish to the cast pot and prevents any unwanted protrusions or rough edges. In some cases, a specialized tool called a riser cutter is used to trim away the excess aluminum from areas where it acts as a reservoir to compensate for shrinkage during cooling. Proper removal of excess material helps achieve a smoother final product, reducing the need for additional grinding or polishing. After allowing the molten aluminum to cool for a few seconds, the metal begins to solidify, taking the shape of the mold. At this point, the molds can be carefully separated to reveal the newly formed pot. Workers must ensure the aluminum is solid enough to retain its shape, but not yet fully hardened, which makes it easier to detach the mold parts without damaging the pot. The molds are gently pried apart using levers or handled tools, paying special attention to avoid warping or breaking the cast piece. Proper timing during this step ensures the aluminum has cooled sufficiently for safe handling while still allowing some flexibility for easy mold removal. Flames are applied to the molds to heat them, causing the metal to expand slightly due to thermal expansion. Once the molds are heated, they are allowed to cool, leading to contraction. This expansion and contraction cycle loosens the mold's grip on the pot, making removal smoother and easier. Making a kitchen knife in the sanmai style is a process that combines traditional craftsmanship with precision. Sanmai, which means 3 layers in Japanese, involves sandwiching a hard steel core between 2 softer steel layers. The material. This involves drawing out the billet, which is done by heating the steel and hammering it to the desired thickness. The goal is to achieve a uniform thickness across the blade, ensuring that the steel core remains centered within the softer outer layers. This process requires careful control of temperature and force to avoid deforming the steel or disrupting the alignment of the layers. With the steel thinned out, the blade begins to take shape. The next step is to forge a tip onto the blade. This involves heating the end of the billet and using a hammer to taper it into a pointed shape. The tip is a critical part of the knife's design, affecting both its functionality and appearance. Careful forging ensures that the tip is strong and aligned with the rest of the blade. Before the blade is fully shaped, it's common to stamp it with a maker's mark or logo. Grinding the bevels is where the blade begins to take its final shape. Using a belt grinder, the blade is ground down from the spine to the edge, creating a bevel. This step requires precision to ensure that the bevels are symmetrical and that the hard steel core is properly exposed along the cutting edge. The tang is the portion of the blade that extends into the handle. Shaping the tang involves forging and grinding it to the appropriate length and thickness to fit securely within the handle. A well-shaped tang provides balance and stability to the knife, making it comfortable to use. To secure the tang firmly in the handle, the tang is heated and burned into the handle material, creating a snug fit. This traditional method ensures a tight bond between the blade and the handle without the need for adhesives. Once the tang is securely in place, the handle is shaped. This involves sanding and polishing the handle material. A torch is often used to add finishing touches to the handle, darkening the wood or adding a unique pattern. Use a coffee bath to enhance the contrast between the different steel layers. The blade is often given an etching treatment, a coffee bath. The acid in the coffee reacts with the steel, darkening the softer outer layers and making the hard core stand out. This step not only highlights the sanmai construction, but also adds an artistic element to the blade. The final step is to sharpen the edge once more, ensuring it's razor sharp and ready for use. This last sharpening polishes the edge and ensures that the knife performs exceptionally well in the kitchen. Making a sanmai kitchen knife is a complex process that requires skill and attention to detail. Each step contributes to the knife's performance and aesthetic, resulting in a tool that is both beautiful and functional. Heating metal in a forge involves placing the metal in a high-temperature furnace, typically fueled by coal, charcoal, or gas. The metal is heated until it becomes malleable, usually glowing orange or yellow. Proper temperature control is crucial, as overheating can weaken the metal, while underheating makes it difficult to shape. Once the metal is heated to the right temperature in the forge, it becomes malleable and ready for shaping. The blacksmith removes the hot metal from the forge using tongs and places it on an anvil. The anvil serves as a solid work surface against which the metal can be hammered. Hammering is a critical step in the blacksmithing process. Using a variety of hammers, from heavier sledgehammers to more delicate ball-peen hammers, the blacksmith strikes the metal to shape it. The force and precision of each hammer blow are crucial. Too much force can deform or crack the metal, while too little might not achieve the desired shape. Hammering is often done in stages, with the blacksmith reheating the metal between stages to maintain its workability. The blacksmith uses specific hammering techniques to achieve different shapes. The blacksmith must work quickly and efficiently as the metal cools and hardens rapidly, becoming less malleable. Ensuring alignment is vital to the structural integrity and functionality of the forged item. Whether the piece is a blade, tool, or decorative item, components must be aligned properly. This process begins during the initial hammering, where the blacksmith carefully observes and adjusts the metal to prevent warping or twisting. For items with multiple parts, tools with handles, or swords with hilts, alignment involves ensuring that all pieces fit together seamlessly. This often requires multiple checks and adjustments during the forging process. For example, a blade's tang, the part that fits into the handle, must be straight and correctly aligned to ensure the handle fits securely. The blacksmith uses various tools to check alignment, such as straight edges, squares, and levels. They may also use visual checks, comparing the piece against known straight surfaces or aligning it with other components. If misalignment is detected, the blacksmith may need to reheat the metal and adjust it with gentle hammering or bending until it is correct. Proper alignment is crucial for both aesthetic and functional reasons. After the metal has been shaped and aligned, it often has rough edges, scale, a layer of oxidized metal, and uneven surfaces from the hammering process. The first step in finishing is filing and grinding. The blacksmith uses files of various sizes and shapes to smooth out rough edges and remove excess material. For many tools, blades, or other functional items, heat treatment is a critical finishing step. The blacksmith heats the piece to a specific temperature and then rapidly cools it, usually in water, oil, or air, a process known as quenching. This hardens the metal, increasing its strength and wear resistance. After quenching, the piece may be too hard and brittle, so it is often tempered by reheating to a lower temperature and allowing it to cool slowly. Tempering reduces brittleness while maintaining the necessary hardness, making the metal more durable for its intended use. Final assembly and inspection for items with multiple components, tools with handles or knives with hilts. The final assembly takes place after polishing and heat treatment. Components are fitted together, often with additional fastening, riveting, or adhesive. Once assembled, the blacksmith inspects the piece for any imperfections or misalignments that might have been missed during earlier stages. Upset forging increases the diameter of a metal rod by compressing it, forming strong bolt heads through localized deformation. Machining is a crucial step in manufacturing hammerhead T-bolts, where precision tools remove material from the forged blank to achieve the required dimensions, tolerances, and surface finish. This process may involve turning, milling, drilling, or grinding, depending on the bolt's design. Machining ensures that the bolt's shaft is straight, the head is properly shaped, and the surfaces are smooth and clean. Roll threading is a cold-forming process where threads are created by displacing material rather than cutting it. In this method, the bolt shaft is rolled between two hardened dies that have the thread pattern engraved on them. As the dies press into the metal, the material is plastically deformed, flowing into the thread shape. This process strengthens the threads by refining the grain structure of the metal, leading to improved fatigue resistance and durability. Roll threading is also faster and produces a smoother, more precise thread compared to traditional cutting methods, making it ideal for high-strength bolts like hammerhead T-bolts. Packing involves inspecting bolts for quality, counting, and securely packaging them to prevent damage during transport and ensure safe delivery. A knife is made. The crafting process creating a knife is an intricate process that blends artistry with precise technical skills. A knife isn't just a tool, it is an extension of the craftsman's vision and expertise. This guide outlines the essential steps to make a high-quality knife using at-home iron carbon steel. The process includes shaping, hardening, and finishing, each step carefully designed to produce a durable and aesthetically pleasing blade. Choosing the right steel. At-home iron, the first step in knife making, is selecting the appropriate steel. At-home iron, a high-carbon steel, is an excellent choice due to its toughness, wear resistance, and ability to hold a sharp edge. This steel is well suited for both professional and hobbyist knife makers because it balances ease of shaping with superior performance. Heating the metal, typically carbon steel, is first heated in a forge until it reaches a red-hot, malleable state, usually around 800 degrees Celsius, 1,472 degrees Fahrenheit. At this temperature, the steel is soft enough to be shaped without cracking, but still retains enough rigidity to maintain its form. Once the metal is adequately heated, the blacksmith removes it from the forge and places it on an anvil. Using a hammer, the blacksmith begins to strike the metal with controlled, even blows. The force of the hammer spreads and compresses the metal, thinning it out and extending it into the desired shape. The hammering process requires precision and rhythm. The blacksmith must work quickly and efficiently as the metal cools and hardens rapidly. As the metal cools, it becomes more difficult to shape, so it may need to be reheated several times throughout the process. Controlling thickness and shape during the flattening process, the blacksmith monitors the blade's thickness and shape, ensuring it tapers correctly from spine to edge and from handle to tip. Consistent hammering helps maintain an even thickness and avoid unwanted warping. Shaping the handle and tip. Once the steel is selected, the first physical step in the crafting process is shaping the handle. The handle's design is critical for comfort and usability, so it must be ergonomically designed to fit comfortably in the hand. Using a grinder or a file, the steel is shaped into the rough form of the handle. Attention to detail at this stage ensures that the final product will not only look good, but also be practical in use. Next, the knife's tip is shaped. The tip's shape depends on the intended use of the knife, whether it's for slicing, piercing, or general purpose use. A drop point or a clip point is often chosen for versatility. This step involves careful grinding and filing to create a precise point that will meet the knife's functional needs. Once the blade and patterns are complete, the next step is to file out any rough edges and imperfections. This filing process refines the blade's shape and ensures a smooth finish. The tang, the portion of the blade that extends into the handle, may also be extended at this stage. Start with the coarse grit side of the stone to remove nicks and reshape the edge. Hold the knife at a consistent angle, typically 15 to 20 degrees, and draw the blade across the stone in a sweeping motion from heel to tip. Repeat this process on both sides of the blade, ensuring even pressure. Once the edge is reformed, switch to the fine grit side of the stone to hone the blade. This step refines the edge, making it sharp and smooth. Again, maintain a consistent angle and apply even strokes on both sides. After sharpening, you may use a leather strop to polish the edge, removing any remaining burrs and giving the blade a razor-sharp finish. Proper knife sharpening ensures the blade remains effective and prolongs its lifespan. Metal cutting with an oxygen lance. Metal cutting with an oxygen lance is a powerful method widely used in heavy industries to sever large, dense materials like cast iron, steel, and other metals. The oxygen lance, essentially a tube through which pure oxygen is blown, is ignited to produce an extremely high-temperature flame capable of melting through metal. When cutting a large cast iron shaft, one weighing 16 tons, the process begins by positioning the oxygen lance at the desired cutting point. The lance is held by a specialized holder designed to withstand the intense heat generated during the operation. The tip of the lance, where the oxygen exits, is ignited, creating a flame that can reach temperatures as high as 3,500 degrees Celsius, 6,332 degrees Fahrenheit. The lance burns through the metal by reacting with the material, generating additional heat through the exothermic reaction between the oxygen and the metal. This reaction allows the lance to cut through even the thickest sections of metal efficiently. Depending on the size and type of the metal being cut, the lance can burn for an average of 3.5 minutes per session, which is usually sufficient to make significant cuts or completely sever a portion of the material. The oxygen lance cutting technique is particularly valuable for dismantling large industrial structures, processing scrap metal, or modifying heavy equipment. Its ability to cut through metal that would otherwise be too thick or cumbersome for other cutting methods makes it an indispensable tool in heavy industries. However, due to the extreme temperatures and the reactive nature of the process, it requires careful handling and precise control to ensure safety and efficiency. Horn Glass Industries AG has been building glass melting plants globally for over 130 years. They offer a complete system from planning to installation, providing customized solutions for different types of glass production. The heart of their system is the furnace, which can melt between 30 and 500 tons of glass per day. Their furnaces use regenerative end-fired technology, which is efficient and flexible. Glass melting furnace regenerator Forhearth. Low energy consumption, low emission values, high flexibility during production changes, 30 to 500 TD. Reduction of dust by batch piles, by carefully managing and piling raw materials. Reduction of heat losses due to closed doghouse. A closed doghouse design prevents heat escape from the furnace. Precise adjustment of flame formation. Horn glass furnaces allow operators to fine-tune flame shape and intensity, comfortable control of velocity and mixing impulse. The system enables external adjustments to flame velocity and mixing dynamics, low NOx formation. Advanced burner technology minimizes nitrogen oxide, NOx emissions during combustion. Heat recovery. Horn glass furnaces employ regenerators to capture and reuse heat from exhaust gases, enhancing overall energy efficiency by significantly reducing the need for additional fuel during operation. Preheating the air. The recovered heat is utilized to preheat the combustion air before it enters the furnace, optimizing the burning process and further reducing energy consumption. Port control or individual burner control. Horn glass furnaces allow for precise management of each burner or port, electric or pneumatic drive for valves. The furnaces are equipped with electric or pneumatic valve drives, temperature and pressure measuring for compensation. Integrated sensors monitor temperature and pressure within the furnace. Increased melting output and stabilization of glass flow. Horn glass furnaces use advanced electric boosting and precise control technologies to enhance melting capacity while ensuring a steady and uniform glass flow. Reduced emissions. Optimized combustion processes and efficient heat recovery systems significantly lower harmful emissions, contributing to a more sustainable and eco-friendly glass production process. Increased glass quality. The precise control of temperature, flow, and composition results in higher quality glass with fewer defects, ensuring superior clarity and consistency in the final product.